So hi, I'm Sharon, a data scientist in PayPal for almost 4 years, specializing in fraud detection data science solutions. And today I'm going to talk about how sometimes we can get blinded by our own models when we're working on a next version of a model that is already taking action in the real world, and offer a semi-supervised learning approach to deal with it. So as many of you probably know, PayPal is a payment platform that connects between consumers and merchants. It has more than 280 million active users, operates in more than 200 markets, in more than 100 currencies. Whenever you pay with PayPal, you know that you're secured no matter what issue may come up later with the transaction itself, with the account. Your money is secured. Outside of PayPal, there are hackers, or like we call them, fraudsters, that keep trying to get username and passwords through many different ways. Just recently, there was phishing text messages sent here in Israel. And every now and then we see this kind of headlines of breach to some poorly secured website, not PayPal, of course, some other website that someone hacked into and just took out hundreds of millions of usernames and passwords. The fraudsters take these usernames and passwords and they want to turn it into money. So to do that, they try to attack many different companies, including PayPal. And they do that by logging into a good, legitimate, valid account and trying to buy something or transfer money to themselves. So of course, the vast majority of transactions in PayPal are good, legitimate transactions. However, in a case where did a fraudster manage to go into an account and make a transaction, the customer would receive an email about that transaction and would be able to go online to PayPal website and file a claim saying, I don't recognize this, I never did this transaction, it wasn't me. Someone from PayPal would review this, and in case the claim is justified, the claim would be approved, and the customer would get her money back. So from the customer perspective, everything is good, her money is secured. From PayPal perspective, obviously it's a loss. It's something that we would like to reduce as much as possible. And from data science perspective, we can look at it actually as a label. If we know that someone filed a claim and the claim was justified, verified by our agents, we now know that this transaction wasn't a good transaction. It was a bad transaction, fraudulent transaction. So once we have these labels for transactions, we can train a model. Let's train a model and try to stop these unauthorized transactions. At the first time we're doing this, it can be like any Kaggle-like challenge or data hack, where we have a bunch of features and a label, and we're working our magic to make a good prediction. After we finished building our model, we're releasing it to live. And here is a mock-up distribution of how our model score would look in live over the two different populations I've mentioned, the good population, the good valid transactions, and the bad population, the bad transactions. So here we can see the model score, and we have a density distribution of the good population in green. You see most of it get a low score, around 0, and the bad population, which mostly gets a high score. We give this model to our analysts, and they look and say, okay, let's take this part of the population, We see that most of it is very bad. And let's stop these transactions. Let's prevent them from happening at the begin with. So this is a good decision for PayPal. But if you think about it from a data science perspective, all of these transactions are now actually become unlabeled transactions. They become a big question mark. Because if we stop the transaction and it never happened, no one would ever file a claim on it and it will never get labeled as bad. So all of these transactions just become this big question mark of unlabeled population. You may think to yourself, okay, so maybe let's do some A/B testing, some control group, something like that. But actually, there are many cases where we cannot do that. It's easy to think about it when we think about a medical case where you're not going to prevent a medicine to someone just to see how it goes. So it is something that is very interesting to consider. So we have this chunk of population, and we know it's a big question mark, but when will it matter? One use case would be when we're working on a next version of a model. Let's say there has been some time and the population has changed a little and we have some new technologies and we want to create a new version for the live model. We want to create a better version. So what will be a better version? First, we want to catch most of the bad cases that are getting caught today. We want to do that with improved accuracy. And we want to offer some incremental value, meaning we want to catch bad cases that were missed by the previous model. If we're mapping our problem back to the data science world, we know that in general we can divide the problems into supervised learning, where we have a label and we're trying to predict it, trying to divide the data. And cases where we don't have a label, the unsupervised learning cases, where we're trying to cluster together, group together many different records. In this case, we're in the semi-supervised learning because we do have some labels from those bad transactions that got past our model, but we also have a lot of cases that are unlabeled. One approach to deal with this problem would be to reduce it back to be a supervised learning problem. This may be the trivial first approach that would come up to mind, and it will be to just ignore that population, ignore that big question mark, and just focus and train our model over a good and bad population only, without that big declines question mark population. The good thing about this approach is that we will have a very clean signal. Whatever is good, whatever is bad, and it's clean. It will be easy to measure because each record has a label. So we can just use whatever classification matrix we like to use, precision, recall, etc. However, we may be missing some strong signals within the data. We know that declines population, that affected population, is a relatively bad population. And if we're ignoring it, we may miss the exact signals we want our model to look for, we want our model to train on. That would mean that we will offer only incremental value. We'll be able to catch cases that never caught before, but not necessarily catch cases that were already caught. To better understand how this works, we can look again at the model distribution from before, but now it's after we took that decision. We have this policy when we want to decline transactions that got a score 0.6 and above. Of course, I'm simplifying it for our talk today. And now, if we look at the two populations, instead of looking at the good and bad, we're looking now only on good and declines. So the good population still distributes pretty similarly. Most cases get a low score. But and the declined population is cases that got 0.6 and above, and we don't know if they're good or bad. If we would have trained the model only on good and bad, without that declines population, our model score distribution would look something like this, where maybe the good cases are still being identified by our model, but you can see that the declines cases have quite similar distribution to the good cases. And if you think about it, it actually makes a lot of sense, right? If we didn't train on these cases, why would our model know how to identify them? And by taking this approach, we can find ourselves in some cycle where we train a model, we release it to live, it starts taking decision in live. We then train a new model over good and bad only, over ignoring the affected population. And then when we're releasing our new version to live, we would later find out that we got blinded by our own model, and we are missing cases that our previous model caught before. We can then train another model to identify those cases, yet again to be blinded and not find the cases that our latest model caught. So when this simple approach can still be useful, it can be useful when you have a very small affected population and you know for some reason that it's okay to ignore it and you have enough signals within your data. Another thing that may come up to mind, another approach, again, to reduce back the problem to supervised learning, would be somewhat the exact opposite. To consider all the declines just as bad, to give them the label 1. This way, we now know that our model is actually exposed to all the signals that are within the data. It's covering both the existing population, also incremental population. It's again very easy to measure. We have a label per record. However, it will be very overfitted to our existing model. So maybe we can take this approach if we have some external knowledge that our existing model is currently taking actions with a very high precision. If we know that all the declines population are actually, let's say 95% of them are actually bad, so maybe we can just consider them as bad and run our supervised learning model. However, it's not always the case. It can be because how the population has changed over time, or maybe your model was used in different ways than you planned. And you can find yourself in cases where that precision is no longer as strong as it used to be when you just released your model. So what can we do if we cannot just reduce it back to be supervised learning problems? Some examples from the literature. These are just a few. One of them is to create artificial input. We can take our labeled data and use it in order to generate new artificial data by having small perturbations over our input data. This may be useful in other domains. In the fraud domain, a simple small perturbation in our features can be exactly the difference between a fraud case and non-fraud case. Other two approaches to deal with the semi-supervised learning case can be self-labeling or weak supervision. Both of these methods are taking the labeled sample and using it in order to label the unlabeled part. In self-labeling, maybe some of you remember that Nofal from PayPal talked about it last year. You take a seed as like the label set you have, you train a model over that seed, and then use the model that you trained in order to label the unlabeled part. This is one approach. Another approach, the weak supervision, is where you have weak learners that together can be used at ensemble to predict over the unlabeled part and determine its label. So both of these approaches can be very useful, and actually we've used them in some projects in PayPal. However, they can be very time-consuming and maybe a project of their own. So in case we have a limited time, we can try maybe a different, simpler approach, and this is maybe the reason this talk is today. So in order to overcome a problem in a simpler manner, we would first need to better understand how this declines population look like. And for that, we can use some statistics. So if we think about it, that declines population, what we're trying to understand is what it's the precision of that population, or the bad rate of that population. And that is actually a proportion. So we can use the proportion estimator in order to estimate that. So how do we do it? We can use it, do it by manual labeling. And let's say we initially labeled just 100 cases, and we saw that 72 cases out of them were bad cases. So now we can say maybe our precision, our bad rate is 72%. Well, I don't know, is 100 is enough? It sounds like a low number. Maybe I want 1 million cases to be manually viewed. In the fraud domain, each case is reviewed by an expert. So it's quite expensive, and we want to make sure that we're taking the right amount of cases to be reviewed. And for that, we again can go to statistics and use the minimal sample size equation. In this equation, we can use our initial proportion estimator, this 72%, together with some predefined confidence level and margin of error in order to calculate what is the minimal sample size needed for our proportion estimator. So in this example, let's say that I want to know in a confidence level of 95%, where my margin of error is plus minus 2. I want to estimate my proportion. So I'm using this equation, and I see I need 932 cases. I can do this in an iterative manner. Each time that I have a bunch of new cases, I can recalculate my proportion estimator and then recalculate my minimal sample size, etc., etc. And if I don't have any initial proportion estimator, I can always just use 50%, because that would guarantee the highest number of minimal sample size. So in addition to just get this number, to know what is the minimal sample size needed, we can use this equation also to better understand the trade-offs of reviewing more cases. For example, if we're just changing the margin of error to be plus minus 5, we can see that the sample size needed drops significantly to be 150. So we can better understand what is the implication of manually labeling less or more cases. So we can do this process, and we can actually do it to different score bands. What do I mean? We know that our initial model, we took cases that got 0.6 and above, and it makes sense that when the model score is higher, the bad rate, the precision is also higher. So we can have this process per different score bands, 0.8 to 0.9, etc., etc. After we have these proportion estimators, we can use them for the model training. So when we're training our model, we're trying to leverage the tools that we have. In this case, we're using the label and the weight in order to sophisticatedly expose the signals within the data, the signals within the declines population, to our model. So here are two options for this model training. For example, we can again look at the declines and label all of them as bad. However, in order to differentiate between the different declines, we can use the weights. We can assign for each decline the proportion estimator as the weight of that decline. In that case, this decline would be exposed to the model in a way that correlates with how likely that decline is to be bad. So let's say it has a 70% chance of being bad, so it will get a weight of 70%. If we have another decline that is less likely, it will be less exposed to the model. This is one option. Another option is to treat the labels in a way that would be to have a bootstrap process where we're using the proportion estimator as a base. What do I mean? We have many models, tree-based models or neural nets, where each record is seen by the model multiple times. And then we can use that quality, and each time that the record is being exposed to the model, we can label it based on the proportion estimator as the probability for the label. So if our proportion estimator is 70%, that decline would have 70% chance of getting label 1 and 30% of getting label 0. In this case, by having this bootstrap process, we already expose the model to the declines population in a mixture way, so we don't need to use any weights, and we can just set them all to equal. So these are just two options on how we can have this mixture of exposing the decline signals, but not taking one of the two extreme approaches we discussed earlier. And maybe you have already thought of some other ways to make this mixture. But actually the trickiest part is how to measure our model, how to evaluate it. Because we know that the way we evaluate the model would eventually determine which spec we'll choose. It will actually make the difference of which model we will choose. So for that, what we're proposing today is to have evaluation methods that are combined of many different groups that together encompass the problem complexity. So the first set of matrix would be a set of matrix over the good and bad population only. Meaning I'm again ignoring that declines population and measuring myself only on the good and bad population. By measuring, I mean all the regular classification matrix. And this group of matrix would help me understand how my model is performing incrementally, how many new cases it can catch. In order not to miss the declines population, after I hope I convinced you it's not a good thing to do, we can use those manually labeled cases that we used in the proportion estimator and again calculate classification matrix over that group. So this way we get a very accurate matrix because we know that each case was manually labeled. But obviously, it's over a very small sample, and it can get overfitted to that small sample. So in order to have another view over the client's population, over a bigger population, we can actually look at the problem as a regression problem instead of a classification problem. And in this regression problem, we would try to predict 0 for the good cases, 1 for the bad cases, and for the declines cases, we would like to predict its proportion estimator, its probability to be bad. This way, we would get a calibrated model where we have a score that represents how likely this case is to be bad. And it will enable our model to be exposed to those signals within the decline population, but in a subtle way, not an extreme way. So taking all of these groups of matrix together would give us a good view on our model and would help us understand how it would actually perform in live once we will replace the model that is already taking action. So to sum up the different approaches that we discussed, we can look at it based on the proportion estimator. In case we went and had our estimator and we saw that the decline's precision, the decline's bad rate is very, very high, we can just treat them as bad and have our supervised learning problem. On the other hand, if for some reason the proportion estimator would be very low, we have very low precision, or it's just the population is very small, we can just ignore the declines. But if we're somewhere in the middle, the approach that we introduced today, the proportion estimator-based approach, may just be what you need. So thank you for listening. If there are any questions. Okay, so I'll start with the second question. The second question is why not just use active learning? Active learning is where you have unlabeled data and you take only the cases that the model had a hard time to label, and you're trying to manually label them. The reason for not using active learning in this case is because we have quite a big group of labeled data, and once you have, let's say, more than a few thousands, so whatever small label data you input the model, it will be much harder to influence our model. So I agree in the cases where you have very, very, very little label data, that can be the case. And regarding if we don't know about people that got declined.
Yeah, if it was declined and nobody contacted to complain, it's actually, he had a good reason. It's probably indeed malicious.
So it can be an interesting lead for another way to label. I agree. I do think that, I'll say what you said. You said if someone gets declined and they didn't call us angry about the fact they got declined, we can know it was a bad transaction. I think in many cases people would just use a credit card instead of PayPal, so it's hard to use that as a label. Okay, thank you so much.